Well, I know there's Japanese. Oh, these are just oh, yeah. Oh, yeah. When they're together, like this one here.
I don't hear too much talking between neighbors, so maybe we'll just go ahead and get started. So, first of all, does everyone have 2.2, the photocopy 2.2? Okay. So, before I turn to these questions, I just wanted to highlight the general question we're asking today, which is, when is a child well-behaved? No, I'm just kidding. Not children. I think we all know when a child is well-behaved and when a child is not well-behaved. What I mean is, when is a function well-behaved? So what does a nice function look like, right? And I think we'd all agree that if you look at a graph and you saw a function, you'd like to see something that looks like that. You know, it's just like, oh, that's so nice. It's nice, smooth, continuous. It does something. Maybe it's a parabola. Maybe it's a straight line. But, you know, in math, we have lots of other types of functions, too. We have something called a step function. Is a step function very well behaved? It looks like this. Have you ever seen a step function? Maybe you have. Oh, maybe you have. Maybe you haven't. But it looks like that. So it looks like you're walking upstairs. Is that a well-behaved function? If you saw a graph and it looked like this, would you say that's a well-behaved function? No, probably not. And if you saw a function and it looked like this, you would probably all say, no, that's not very well-behaved at all. So part of what we're going for here is, when do you know a function is well-behaved and when do you know it isn't? And part of that is just a gut feeling you have. Like you look at something like that, you're like, yeah, that's a very well-behaved function. It's a nice, simple, smooth line. And you look at something like this, and you're like, gosh, I hope I don't have to answer any questions about that graph. And this one, you're like, well, what the heck? It jumps around all the time. And like that has a little hole in it, and that has a jump discontinuity. So in calculus, before we can use our tools of derivatives and integrals, we have to know that we're at least looking at a graph that is well-behaved. And a well-behaved graph, we use the word continuous. A well-behaved graph has to be continuous, meaning you could draw the whole thing without picking up your pencil. As soon as you've got some jumps or you've got some holes, it's no longer well-behaved, and you can't necessarily apply the tools of calculus. So looking at a graph, that's easy enough. You know, not well-behaved, well-behaved, not well-behaved, well-behaved. But now how would you do it if you were just looking at the equation? You know, what if you weren't allowed to look at a graph and all I did was give you a function f of x? How would you know if that was well-behaved or not? So that's part of what we're talking about. That's the big picture of what we're talking about from last class and this class. Okay, so the first question, when we say a function is continuous, what intuitive idea do we have in our minds? Oh, how about Jacob?
You don't lift up your pencil?
Yeah, you don't have to lift up your pencil, right? It's just a nice smooth curve. It's a function, and there's no breaks in it or no jumps or no holes. Okay, what are two common types of discontinuities? We used these words the other day when looking at something like this. What's one type of discontinuity, Brandon? I don't even know if we labeled it specifically, but one type is when it goes like from here to here. What did we call that?
Jumps.
A jump discontinuity. And the other type of discontinuity was like this, when it's just a hole. Yeah, it's a hole. So you can have a hole discontinuity, a jump discontinuity. There's other types of discontinuities we'll see as we move along. But that would mean that the child is not well behaved. I mean, function is not well behaved. So how do you recognize these types of discontinuities in an equation? Well, that's a big question. How do I know if a function is well behaved or not? So let's just say I gave you f of x equals x squared minus 7. Would you say that that's a well behaved function? It is, because what is it? It's just a parabola, right? And a parabola is nice and smooth, and you can draw it without looking at your pencil. What about the minute I divide it by x plus 2? Now, is that a well-behaved function? Is it still well-behaved? I mean, it still looks relatively nice. Well, what could go wrong here? You could have a hole or an asymptote. Why? What could go wrong in this equation? I just turned it into a fraction by giving it a denominator. What could go wrong in the denominator? It could be 0. The denominator could be 0. Specifically, what happens if I plugged in the value -2 into that function? I would get -2 squared minus 7 all over -2 plus 2, and then we would have 4 minus 7, -3 over 0, which is undefined, and that's a real problem. Now, that's how you would analyze a function to see if it's well behaved or not. You would look for any time a denominator is equal to 0, or any time you're square rooting a negative, right? Those are the two things you're not allowed to do. Those are no-nos for bad children, bad functions. I don't know why I keep saying children. It's just supposed to be a joke, folks. A no-no would be dividing by 0 or square rooting a negative, right? So anytime you divide by 0, square root a negative, there's going to be a problem with your graph. So specifically, let me just show you the random example I just made up. Let's see here, we'll go to Desmos, my favorite website. They don't even pay me. They should pay me. I recommend it all the time. So here's x, what is it? X squared minus 7? Yeah. All over x plus 2. There we go. So do we see the problem? Is that a smooth and continuous graph? If I started over here, I'd be drawing, oops, down to -infinity, discontinuity. And then I have to jump from -infinity all the way up to +infinity in order to keep drawing my graph. That's a pretty big jump. How tall is the jump from -infinity to +infinity? It's a really long jump, right? So this graph is discontinuous because it has two different pieces. And how did we know that it was discontinuous? Because it had a denominator that could be 0. So these are the two ideas we're looking at. How do we figure out when a graph is not well behaved? How do you see that in a graph? It's kind of obvious. How do you find it in an equation? A little less obvious. So that's what we're looking for. The end result of all of this is that in calculus, you really just study well-behaved functions. Like once you know how to eliminate all the bad behaving children functions, you just study the good behaving functions and you apply calculus to them. Okay, I think I have one more question. What do you need to do to a function if the output is 0 divided by 0? So let's say that I had this function x squared plus 6x plus 9 all over x plus 3, and I want to find the limit as x approaches -3. Can I just plug -3 into this function? What would happen if I did? Yeah, it'd be undefined. The bottom -3 plus 3 is 0. I still have to plug -3 up there. That would be 9 minus 18 plus, that's also 0. So I don't know what the value of this is yet. So what do I have to do to this whole thing? What is it?
Foil the top.
Not FOIL, but factor the top. And once I factor the top, then I would see x plus 3 times x plus 3. And after factoring the top, then what can I do?
Cancel.
Yeah, you can cancel, you can simplify. And now you have x plus 3, which you are allowed to now plug -3 into this expression. -3 plus 3 is just 0, and that's fine. The limit can be 0. It could be that the function is approaching 0. So that's what we looked at last time, is how do we analyze a function if it does have a problem with it? And how do we still say something meaningful about it? Okay, so that was the last class. We didn't quite finish section 2.2. We'll finish it right now. Otherwise, here we are, August 29th. We're going to start section 2.3. You'll notice that we have 2.3 on both today and when we get back on Wednesday. So we're starting 2.3 today. You have no school on Monday. I know you're all very sad about that. Probably we're all going to go home on Monday and cry a little bit because we're not here. But then Wednesday will come and we'll come back. Okay, what's due today? No, nothing, because today's Wednesday, right? But on Monday, even though it's a holiday, keep in mind that even though it's a holiday, you still have 2.1 and 2.2 due on the holiday. Now you might say, Mr. G, that's not fair. I don't want to do homework on a holiday. And I'll say, no problem, just do it on Sunday. You know, finish by Sunday. That way Monday is a holiday and you can do nothing. Okay, before we start class, I have a joke for you. This is one of my all-time favorites. What did the Buddhist ask the hot dog vendor? What did the Buddhist ask the hot dog vendor? Make me one with everything. Yeah? make me one with everything. Thank you very much. Thank you very much. That was very kind of you. Okay, so here we are. Let's finish 2.2, and then we're going to do an Excel activity. We're going to finally use our computers, and we'll start talking about 2.3. So this is where we were on your packet, right? And everybody has already told me that they have the 2.2 packet, so go ahead and open up to, I believe, the very last page. Yeah, it is the very last page. Well, the second to last page, where it says, what are the 3 conditions for continuity? All right. So we're going to bring all this together and say, when can we say a function is well behaved? And a function is well behaved when it's continuous. And a function is continuous if you can draw it with your pencil without picking it up. But there's no mathematically precise way to say that in equations. How do you write an equation that says, draw it with your picture or with your pencil, but don't pick up your pencil? So mathematicians came up with this way of describing a well-behaved function. And the 3 conditions of continuity are here. So we're going to do all this together using this example. So you have 3 lines where you can write this down. And you also have a little bit of space there. Oh, thank you very much. What was your name again? Lisette. Notice that I emailed all of you the notes for this section, and she already printed it out. So this is actually what I'd like your paper to end up looking like. You're going to draw a little graph up here, and then you're going to write down these notes with me. Okay? So let's all start by making a graph. I should draw this with you. We're going to talk about when a graph is continuous. So I'll draw it over here because that's where I had it on Lisette's. And we'll just draw some curvy little thing and a point. And Lisette, just to use your numbers, since I already did, what numbers did I use? 4 and 6? Okay. So let's say we're approaching 4 on the x-axis and 6 on the y-axis. And we'd like to know that that part of the graph right there, just this part of the graph, bloop, right there, bloop, was that part of the graph continuous? Was I able to draw this part of the graph without lifting up my pencil? I won't even worry about the rest of the graph. We're just saying, hey, for that part right there, when x is 4 and y is 6, is that part of the graph continuous? Is it well behaved? So the first condition is that the limit of f of x has to exist. And so that's what you'd write down mathematically, and in quotation marks, I have what it means in simple English. So criterion number 1, the limit of f of x exists. Remember what that means is both fingers have to be approaching the same point, like that. So is that true in this case, that as my fingers move towards each other from the right and from the left, are they approaching the same point? Yes. And in English, you'd say your fingers touch, right? So from both sides of the graph, my fingers are about to touch, and then they do touch. So that's the condition 1, that the limit exists. Just to remind you, folks, we had a limit as x approaches 4 from the left, and we also had a limit as x approaches 4 from the right. So when we say limit as x approaches 4, we mean approaching 4 from both the right and the left simultaneously. So when we just say the limit as x approaches 4, we mean from the right and left. If we just meant left, we'd put a little minus sign to the right of 4. And if we just meant from the right, we'd put a little plus sign. But limit as x approaches 4 in general, that means both fingers. And so that's what this means. The limit exists. Okay, criterion 2, f of a exists. That means that the actual point exists, that there's a value on the graph. So for instance, in terms of an input-output table for this function, if I input 4, what's the output? If I did a table of values for this function and I inputted a 4, what would the output be? 6, right? That would be the output. Because you just go to wherever the point is on that vertical stripe above and below the 4. You just look for where the point is, and there it is. And so the output is 6. So yes, f of a exists. And what that means is there's actually a point somewhere at the x equals 4 vertical stripe. So that's true. And then the third criterion is that that limit that we said existed in condition 1, you know, where our 2 fingers were coming into, and the point that we just said existed, those are actually the same thing. That my fingers are approaching the point, which is the output of the function at that particular value. So in this particular case, we would say yes. If we just looked right in here, we'd say, yep, the graph is nice and continuous because the graph is approaching the same point from both directions, and there's actually a point right there. So I think it would be valuable to look at examples where that could go wrong. What if one of those three things is not correct? And you might want to draw this down, or you might just want to look at it. Either way, let's think about what would condition number 1 look like if it was violated. That limit f(x) does not exist, meaning the fingers don't touch. What would that graph possibly look like? What would I have to draw for a graph where the fingers don't actually zoom into the same spot? Here's some sort of a jump function. So maybe the graph would go like this, and then it would start up here, and it would look like that. So that would be a violation of condition number 1. Condition 1 says that the fingers should come in towards the same point, whereas a jump discontinuity, that limit wouldn't exist. So that's a violation of number 1. These are violations. Boy, that sounds terrible, but I'm going to write the word violations. Violations of the conditions. What about number 2? What would a violation look like of f of a exists? So there's my graph. There's the coordinate 4. What would that look like? That there is no value for the input of 4. That if you did a table of values for x, f of x, and you input 4, and you get out undefined, because theoretically you divided by 0 or you square rooted a negative, what would that look like? It would look like a hole. There's no point anywhere on that vertical stripe where the 4 is. Or, even better, it would look like a asymptote, which is what we were just looking at a second ago. Nowhere along the vertical stripe, x equals 4, is there a point. Because the graph rides this asymptote going up, never reaching 4. And this part of the graph rides that asymptote down, never reaching 4. So both of those are an example of the violation that there is no actual point for the output of 4. And then what would a violation look like for part 3? The limit of f of x does not equal f of a. So what would that look like? That where your fingers are going is not where the actual point is. What's that? Not necessarily a jump, because we are saying that your fingers are approaching the same area. But we're just saying that, that where your fingers are approaching is not where the actual point is. So where would I have to put the point? If it's not right there, where would I put it? It has to be somewhere on this vertical stripe at x equals 4. I could either put it above or below. Either way. In this particular case, let's say I put it all the way up here at 8. In that case, on my table of values, my x, f of x, if I input 4, the output is 8. So yeah, the point does exist. F of a does exist. It's just that it's way up there, and it's not where my fingers are touching. So there you go, folks. Those are the 3 conditions for when a graph is well-behaved. And these are examples of how each of those conditions can be violated. And so going back to my, too bad I already erased all these. When is a function well-behaved? It's only well-behaved if these 3 conditions are met for every single point on the graph. So if your whole graph, you could choose any point on the graph and say that these 3 conditions are met, then the whole graph is well-defined and it's well-behaved. What would you like to ask about that before we move on? That's the definition of a continuous function. And remember, continuous just means well-behaved. Would anyone like to ask any questions before we move on? Yes, Simone.
So I know that you have to turn this in like on the test day, and you want like everything that you write into this. But is it okay that, yes, I'm writing it down, but I don't want to cram everything on one paper? write stuff in my notes and you can.
Oh yeah, sure. You can write it on a line sheet of paper or on your arm, whatever you want to do. Okay, well, what I have now is a couple of examples. So let's just look at the couple of examples together, and you tell me if these functions are well behaved. Now, obviously, for these two examples right here, you could all tell me in a group, are either of these functions well behaved? No, neither of them are well behaved. But now let's be specific about why. Why is this one not behaved? So let's go through the three conditions. Does the limit exist? And remember, what's the friendly definition of limit existing? Your fingers touch. So in this particular case, would your fingers touch? No. So that's a no. I should have read the whole question. The graph below is a function f of x. Which rule for continuity is violated at x equals -1? So we're looking specifically at x equals -1. So first of all, no. The limit doesn't exist because our fingers don't touch. How about condition 2? Is f of a defined? If I look at the vertical stripe at x equals -1, is there a point somewhere there? Yeah, there is a point. It's right there. That would be the output. So yes. As a matter of fact, f of -1 is equal to 2. So that's something I can just read right off the graph. F of -1 is equal to 2. So yeah, it's defined. Again, you can either just write f of -1 equals 2, or you can see it on an input-output table that if you plug in -1, you get 2. And then finally, is the limit, that is where your fingers are touching, is it the same as what the point is? And we would have to say no to that, because our fingers aren't even touching in the first place. So since this limit doesn't even exist, there's no possible way that it could be equal to f of a, because they're different. So overall, we would say this function, it might be well behaved over there, and it might be well behaved over here, but overall this function is not well behaved because there's a point of discontinuity at x equals 1. And why is it a point of discontinuity? Because the limit doesn't exist. And because the limit doesn't equal f of a. Okay, same goes for the next one. So does the limit exist? And again, like in the beginning, you might want to put that English in there. Do the fingers touch? No. Is the point defined at x equals -1? What's the output? 2. So yeah, that point is defined. Yes. F of -1 equals -2. And the third condition, does the limit equal the point? Well, no, because your fingers aren't touching in the first place, so that part can't possibly be true. So that's a no. Okie doke. Oh, were there more? No. That's the end of the packet, right? Okay. So just to kind of wrap that up, when we use calculus, that is derivatives and integrals, you can only use calculus on well-defined, well-behaved functions. And so the first thing that you have to do is ask yourself, is this function continuous? Because only if it's continuous are you allowed to take a derivative or an integral or do calculus. If it's not continuous, then you can't even do a derivative or an integral. So we're kind of like saying, hey, if you want to do calculus, that's fine, but you can only do calculus on well-behaved functions, which are continuous functions. So this is the first task in calculus, is to narrow down which functions we're allowed to look at. We're only allowed to look at continuous functions. Okay. Well, folks, that's it for 2.2. So now you're all equipped to finish the homework for 2.2. And if you have any questions when you're doing your more homework, please feel free to email me. I've continued to get a few more emails from you folks, which is really exciting. I like getting emails. My wife loves it too. Like, we're sitting at dinner, I'm like, hold on, honey, I got an email from a student. And I start replying to the email. All right, well, if anyone doesn't have any other questions for 2.2, then what we're going to do is go back and find this packet. I gave you a packet on like the first or second day of class, and we did the first few pages. It was about slope. But then the last couple pages I said, just hold on to this and we'll do it later. A couple of you might need this. It looked like, what does a derivative find on the very front? Let me see if I have, how many copies do I have? Oh, I have plenty of copies. So who needs a copy? There you go, my friend. And Sarai. Okay, there we go. And Sila. Who else needs one? Anybody else good? Lizette, you got one? Okay, good. So we went all the way through to, differential calculus, this fellow right here. So we're all looking at that one? Okay. So we've kind of already hinted at this, and we've talked about it a little bit, but I want to be even more clear about how Newton and Leibniz invented calculus in the 1600s, and about what makes calculus so different from other fields of study. Remember how I talked about the difference between pre-calculus and calculus? And what was it that we studied in pre-calculus? Things that are straight. So we studied straight objects, straight lines, straight shapes. And then in calculus, we get to study as well things that are curving. Right? They're a little more complicated. They require special tools of calculus. Well, there's one other difference between pre-calculus and calculus. And that is that in pre-calculus, you study finite numbers. Right? So like 12. How many apples do you have? 12. How many sheep are in that field? 13. How many, I don't know, how much money do you have in your bank account? Negative 1,472. Right? These are all finite numbers. Whereas in calculus, we get to study things that are infinitely small, which begs the question, what does it even mean for something to be infinitely small? Is an atom infinitely small? An atom is not infinitely small. It's just a little smaller than us. But it's not infinitely small. What would it even mean to you for something to be infinitely small? If you had a magnifying glass or a microscope and you started zooming in to see it, it's infinitely small. How long would you have to turn the dial to eventually see it? Forever, right? I mean, if it's infinitely small, no matter how long you turn that dial on that microscope, you're never going to see it because it's infinitely small. Or if you're looking at a number, is the number 0.0006 infinitely small? So how many zeros would I have to put before I write down the 6? Yeah, but I mean, can I, if I'm still writing infinitely many zeros, when do I get to write the 6 down? Technically never. But what I'm suggesting to you is that there's a number that goes 0.00000, infinitely many zeros, and then there's a 6 at the end. Of course, that doesn't make too much sense, right? So this is a little philosophical about what is something that is infinitely small. But that is what we will talk about in this course, is things that are infinitely small. And in fact, Newton and Leibniz called them infinitesimals. Infinitesimals. That's what they referred to them as. And so in the late 1600s, early 1700s, when they started writing books and articles about infinitesimals, a lot of people wrote back and were like, this is foolishness. This is nonsense. What's an infinitesimal? Something that's infinitely small but still exists? That's a contradiction, a paradox, is not real. So they did get some flack for it. Okay, we're also going to study things that are infinitely large. So that's probably just your normal intuition. What number is infinitely large? Infinity, right? Just infinity itself. So there's no special symbol for something that's infinitely small, right? I mean, if it's infinitely small, it's not 0, but it's not 0.1 either. It's really small. Okay, so this is another difference between pre-calculus and calculus, is that pre-calculus studies straight things that are finitely big, whereas calculus studies things that are curvy, and we look at things that are infinitely small and infinitely large. And it makes sense. You're allowed to. So here's what we're going to do. Let's take a look at the top. The aim of differential calculus is to find the slope of a curve at a single point. So again, if we were looking at a parabola, and I wanted to know, say, the slope at a single point, what do we call that line if you're finding the slope at a single point? Tangent. So we want to find the slope of a line tangent to a curve at a single point. That's our goal. However, in order to use the slope formula, you need 2 points. Namely, you need to use the formula y2 minus y1, x2 minus x1, which requires 2 coordinates. So that right there would leave you feeling like you're at a standstill. Like, okay, I need to find the slope at 1 point, But in order to use the slope formula, I need 2 points. So that sounds like a contradiction, like it's impossible. However, what Newton and Leibniz did was, with differential calculus, it finds the slope between 2 points that are infinitely close together. This always makes me think of 2 children who are being immature and they're like, I'm not touching you, right? Like, how close can you get and still not touch somebody? Pretty close, right? And so that's what we're saying here is that we're going to find 2 points that are infinitely close together. They're really close, but they're not touching. So our method is, let's find the slope between 2 points that are infinitely close. Because if you can find the slope between 2 points that are infinitely slope, you can go ahead and just call that the tangent slope. You can say that's equal to the slope at a single point. Okay, everybody ready? Here's what we're going to do. The title said it. Find the slope of a curve at the single point x equals 1. So go ahead, find 1, and put that dot on your graph, and go ahead and make a little tiny tangent line slope indicator for what the slope appears to be right there. Does it look like I drew a tangent line to the 1 point? I hope so. That's what I was trying to do. So go ahead on your own paper, make a teeny tiny little slope indicator to suggest what the slope is at the point x equals 1. And by the way, while we're at it, what is that coordinate?
1, 1.
How did you know that we all know it's 1 for the x, but how do you know what the y is?
That was me.
It does? Oh, what do you mean, all those?
Yeah. Oh, yeah, yeah.
Well, that's true. Well, did I not put it on here anywhere? This whole function, so remember this is x, this is y, and this function is f of x equals x squared. So we're looking at the parabola x squared. And so whatever your input is, you calculate your output by calculating f of x, right? Because f of x is the y coordinate, it's the height. So in this particular case, any coordinate on this graph, I'll just put a general coordinate over here. Any coordinate on this graph is x comma x squared, or x comma f of x. So in this particular case, if your input is 1, you square it, and your output is 1. So yeah, that coordinate is 1, 1. So what we're going to do is choose a second coordinate off to the right a little bit. How far to the right are we going to choose a coordinate? I thought we would go all the way to 4. Let's go all the way over to 4, and go up to the graph and find that coordinate. So this function, again, is f of x equals x squared. And we're going to choose a second coordinate way over here. Are these 2 coordinates infinitely close? No. How far apart are they? On the x-axis, how far apart are they? 3. They're 3 units apart. So nowhere near infinitely close. They're really quite far apart from each other. Okay, so what's this coordinate? The input was 4. What's the output? 16. And again, you use the function to calculate the y coordinate. The y coordinate is the output of the function, which is f of x. So the output is 16. Okay, so we have chosen our first 2 coordinates. They are by no means infinitely close together, but they're easy to work with. And what I'm going to do is draw a secant line between them, just so you can see that that's the slope we're about to find. The slope we're about to find is that black slope. Is the slope of the black line equal to the slope of my blue line? Like, remember, we all originally drew a little tangent line that was tangent at a single point. Is the slope of the blue line equal to the slope of the black line? No. The black line is too steep. It's too steep. But it's close, right? I mean, all things considered, it's fairly close. So whatever answer I get right now is an approximation to the true answer. So let's go ahead and do it. Let's find the slope. Remember, this is x1, y1, and this is x2, y2. And so we'll go ahead and calculate our slope, y2 minus y1 over x2 minus x1. And now we have 16 minus 1 over 4 minus 1, which is just 15 over 3, which is 5. It is 5 over 1. So our first slope is 5/1. It's not the same as the slope of the tangent line at x equals 1, but it's close to it. It's in the ballpark. So now here's what I want you all to imagine, and I want you to draw it on your graph. What Newton and Leibniz did was, now we're going to hold this point fixed, and we're going to start sliding this point in, closer and closer and closer and closer until it's infinitely close. Our first slide is we're just going to slide it in to 3. So now we just slid the point from x equals 4 to x equals 3. We slid it a little closer, not infinitely close, but a little closer. And I'm going to go ahead and draw another secant line. And I want you to appreciate, what can you say now about my secant line? Is my second secant line a little closer to the blue secant line? I'm sorry, the blue tangent line? It's better. You'll notice my first secant line was steep. My second secant line is a little less steep, and it's a little closer to the true value of my blue tangent line. So by sliding my point closer, I brought my secant slope closer to my tangent slope. Okay, so now let's do that one. Now this part you'll probably get pretty fast at. You might not even have to keep writing down y2 minus y1, x2 minus x1. Maybe you just know, and it's sometimes what I do is I draw arrows. It's 9 minus 1, 3 minus 1. The 9 minus 1 goes on top. The 3 minus 1 goes on bottom. And that gives us 4/1. Where?
The third subclass. No, down. Right.
Oh, is that a period? That should be a comma. Yeah, thank you. Okay, now I realize that at this point we could all just sit here and plug in all these real quick. But the visual thing I want you to appreciate is what I'm doing up here visually. So everyone, if you're already crunching numbers down here, everyone stop and just look up here as we do the visual again. Let's take this point and now slide it again closer. Now we're going to slide it to x equals 2. And watch again my secant slope. Is my secant slope now even closer to the blue slope? My original secant slope was quite steep. The second one became less steep. And now my third secant slope is even less steep. And wow, it's getting really, really close to the blue tangent slope. And that's what we should be experiencing right now, is that as I choose 2 points that are closer and closer together, the secant slope is becoming really close to the tangent slope. Okay, so we do that computation. And so again, 4 minus 1 over 2 minus 1, and that gives us 3/1, which is 3. Okay, so folks, on your drawing, I hope that you can still do this. Slide that point a little closer. We're going to slide that point to, what, 1.5. So I'm going to slide my blue point down to 1.5. Now I'm looking at the input value of 1.5. Oh, 1.5 is down there. There we go, 1.5. And so now my input value is 1.5. And now if you draw a secant line, I mean, my goodness. My secant line and my blue tangent line are almost indistinguishable. And especially on your paper, it's probably even harder to make a difference between the secant line and the tangent line, but they're really getting close. So now between those two, what do we have? 2.25 minus 1 all over 1.5 minus 1. 1.25 over 0.5, what is that? 2.5 over 1? Okay. Or in other words, that's 5/2. In any case. Okay, now this is really the culminating effect here, folks. Is just watch up here. Now I'm going to slide my point from 1.5 to 1.1. And oh my gosh, now sliding that point in, my 2 blue points are right next to each other, right? And at this point, not you on your paper, not me on my whiteboard, I can no longer tell the difference between my secant line and my original blue tangent line. So the closer I slide those 2 points together, the closer my secant slope is going to be to the true tangent slope. So at this point, there's really not much else to do besides the math. And so we end up with what? 1.21 minus 1 and 1.1 minus 1, which is 0.21 over 0.1, which is 2.1 over 1. And then the last one I can't do because it's on the whiteboard. What is the last one? Is it 2.01 over 1? Did anyone do that one yet? Is that a typo? No, it's not a typo. Yeah, it is 2.1 over 1, right? So everybody, if you look at your slopes, we went from 5, 4, 3, 2.5, 2.1, 2.01. What slope are we approaching? If we kept doing this process, bringing the points closer and closer, what value do you think we'd end up at? 2. 2 is a pretty good guess, and 2 is correct. The actual tangent slope at this point, if you could calculate it, would exactly be 2. And I think that's what you do at the bottom. Predict the slope of the point at 1, 1. Okay, so I hope we all appreciate what we just did. We found the slope at a single point by finding the slope between 2 points that are infinitely close together. And that's the first method of calculus. Taking a derivative, you're finding the slope at a single point by finding the slope of 2 points that are infinitely close together. Any questions about that process? Can I ask for some feedback from you folks? Like, does this seem like tricky, or does it seem like really obvious, or?
No, I think you've explained it pretty well, to be honest.
Okay, so like,
Yeah, I think.
okay, so everybody feels comfortable with this idea. Good. I mean, this is the philosophical underpinning of calculus. So now what we're going to do, go ahead and turn the page. Is this the next page you have?
Yes.
This looks to be the same problem. I think I just printed the wrong thing. I'm gonna get rid of all this. Find the slope of y to find the slope of at the point x equals 1. Yeah, we just did that. So I must be, oh, now I know. Yeah, we're going to do it abstractly now. So now this is going to be a very different process. We're going to do it abstractly. Everybody now, the method is find the slope between x equals 1 and x equals 1 plus h. So h, if you wanted to define h is the distance between our 2 coordinates that are sliding infinitely close together. Okay, so like in the problem that we just did, we did the slope between the point 1 and 4, so h would be 3. And then we did the slope between 1 and 3, so h would be 2. And then we did the slope between 1 and 2, and h would be 1. Then we did the slope between 1 and 1.5, so h would be 1/2. And h is always going to represent the distance between those 2 points. It's just right now we don't want to actually nail down how far apart those 2 points are. We're just going to say that 2 points are h units apart, and what we're going to end up doing is, goal, is take the limit as h approaches 0. We're going to create an algebraic expression that tells us the slope between 2 points that are h units apart, and then we'll take the limit as h approaches 0, just like we took the limit in those other problems that we did yesterday. And by yesterday, I mean Monday. So let's label up our graph. So here's 1. Where should I put 1 plus h? Here's what I'm going to do. I'm going to draw a little arrow to the right. I'm going to say that's h units to the right. And then I'm just going to arbitrarily pick a point and call it 1 plus h. Okay, so I have 2 x values, x equals 1 and x equals 1 plus h. The point 1 plus h is h units to the right of 1. Now let's find the coordinates. So here's a coordinate. Here's my arbitrary coordinate. What are the actual values of those coordinates? And remember, any coordinate can always be thought of as x comma y or x comma f of x. Because remember, f of x represents the y value. So what's the first coordinate? This one's easy. There's just 1, 1. Because you plug in 1 and then you square it. Because remember, our function is y equals x squared. So how about our second coordinate? What's the x coordinate? 1 plus h. Previously it was 4, 3, 2, 1.5, but now it's just 1 plus h, or 1 plus h. And what's the y coordinate? Remember, you find the y coordinate by plugging your x coordinate into the function x squared. So if I have f of x equals x squared, and I want to plug in some value, like 3, I would plug in a 3. And then that would be 3 squared is 9. But I don't want to plug in 3, I want to plug in 1 plus h. So what's my y coordinate? 1 plus h squared. Now that right there is normally, a tricky part. Like you look at this coordinate and it hurts your brain a little bit. Because remember, the 1 plus h is the x coordinate, that's your input, and then the output is calculated by plugging your input into your function x squared. So the output really is 1 plus h squared. Okay, everyone has our 2 coordinates labeled? Now, what we want to find is the tangent line. But that's impossible to find because it's a single point. So instead, we find the secant line. So go ahead and draw a secant line through those 2 points. Let's finish this problem and then we'll take a break. And we'd like to find the slope between those 2. So I'm going to go ahead and label, this is my x1, y1, this is my x2, y2. And we'd like to go ahead and find the slope. So slope is y2 minus y1, x2 minus x1. And now we go ahead and plug everything in. Okay, so we have a little bit of computation to do here. Sadia. That's right? Sadia? Okay, Sadia, what's my y2? 1 plus h squared. And Sila, what's my y1? Yeah, just 1. And then Allison, what's my x2?
1 plus h.
Yeah, just 1 plus h. And then Aldo, what's my x1?
1.
Just 1. Okay, so that represents our slope. All we have to do now is simplify quite a bit. So how do we square 1 plus h squared? What's the definition of squaring something, Michelle? What does it mean to square something? Yeah, so this is really 1 plus h times 1 plus h. And so now how do we do that? Yeah, now we're going to do FOIL. So 1 times, first is 1 times 1. Outer is 1 times h. Inner is 1 times h. And last is h times h, which is h squared. That leaves us with 1 plus 2h plus h squared. I did my work over here in some Scratch workspace. In general, it's a good idea to do Scratch work like that somewhere else, so that now, as we continue to write this out, we can just write it out nice and clean. 1 plus 2h plus h squared minus 1, all over. What happens in the denominator, Efren?
What's canceled?
No, the 1's cancel, and we're just left with h. Okay, what else happens in the numerator? Miss Cheryl, what very nice thing happens in the numerator? What? What really nice thing happens in the numerator?
Oh,
Now the 1's cancel out, and so now we just have 2h plus h squared all over h. Now right now you might feel like we're done because that's looking pretty good, but there's one more thing that we can do in the numerator. What can we do in the numerator? We do want to do some more canceling, but what do you say?
1 over h. H over 1.
H over 1?
H over 1.
I don't think we want to do that. We can factor out an h from the top. Because on the top we have an h we can pull out. So now that's h outside of 2 plus h. And then, Bata, what can we do? Yeah, we can cancel out our h's. And whammo! Now we have this nice expression. It's just 2 plus h. And let's really appreciate what we just found. Maybe by reminding ourselves, what on earth did we just find? We just found the slope between what? Yeah, between 2 points, right? Between a fixed point and an arbitrary point off to the right. So that expression, I'm going to write it down again, m equals 2 plus h is the slope between 1, 1 and an arbitrary coordinate 1 plus h, f of 1 plus h. It's just off to the right a little bit. And so what do I want to do with this coordinate? I want to slide it infinitely close. Now what does that mean to slide this coordinate infinitely close? What am I going to do to h? I'm going to make h smaller and smaller and smaller. How small will I make h? Infinitely small. So what we're going to do now is take the limit as h approaches 0 of the expression 2 plus h. Keep in mind, technically, you can't just make h equal 0. Right? Like, if we had originally done this computation with h equals 0, what would our slope have actually been? If h was 0, this coordinate would have been 1, 1. And had I found the slope between 1, 1 and 1, 1, what would my slope be between 1, 1 and 1, 1? 0. 0 over 0, which is undefined. So technically, we didn't let h equals 0 early on because we wouldn't have calculated a slope at all because it would have been a single point. But now that we're at the very end of the process, doing the limit, now we are allowed to plug in 0 for h. And when we do plug in 0 for h, what do we get? 2. And what was the answer that we got on the previous page? 2. So this might sound like cheating, like, okay, Mr. G, you're not allowed to let h equal 0 in the beginning, but you're allowed to let h equal 0 at the end. And I would say, yeah, that's part of how this process works. So we ended up getting here the same answer that we got by taking lots of individual points and guessing, and now we took an arbitrary point and slid it infinitely close by taking the limit as h approaches 0. Okay, we should take our break. So the time is 11:56. Let's come back at 12:06. Josue, not here. Juliana, not here. Mia, not here. Everybody else here. Hey.
So for the office hours, high school trip,
Oh yeah.
you know,
Oh, you have to be there by 1. Oh, okay, I see. And then, where do you come from before you come here? Oh, so you come straight here.
Yeah.
Okay, so in other words, you come straight here, then you go straight back. Okay, well, you just want to show it to me now? Show me your notes from today, for instance. Hey, Alexis. Oh no, I'm so sorry to hear it. Okay.
I wrote it down in the student's English.
Oh yes, I do remember that. Okay, so for the rest of today, we were actually going to boot up our computers and use Excel. So you should still be able to watch it from the video because it'll be on the screen, and you can try it at home if you have Excel on it. Okay. Okay. I hope you feel better.
Thank you.
Hey, all right. So if you were to come to office hours, I would just sit down and look at all of your work and see the notes you're taking. Oh, goody gumdrops. Okay, that all looks good. Ah, yeah, very nice. Okay. Now, at some point, I still want you to come to my office because otherwise, any number of people could be like, "Well, I just can't make it." So, how about at some point, whenever you're free today or tomorrow, go up to my office and just put a note on the whiteboard. I have a whiteboard outside my door. Just say, Michelle was here. And provided you spell your name with 2 L's, not 1, I'll know it's you. Okay.
And then I also have a thing you're supposed to sign every day out here.
Oh, yeah.
So I don't know if you'd rather me give it to you at the end. Sign it all.
Oh, whenever you want to do that, I suppose at the end is easier. That's what the previous high school students have done. And I'll give you the same deal that I gave them. It's only $1 per signature. So yeah, just bring it at the end when it's due and I'll sign it all. Okay, yeah, go ahead.
Question.
Miss Cheryl. Sorry, Miss Cheryl, what am I just saying? Simone.
Yeah, I was like,
Both of your
do
names are so cool because you got me, Cheryl, and you got Simone, and you sit right next to each other. Sorry, I just got a little
It's
space.
okay.
Simone.
I was like, ooh,
No,
excuse me. So I didn't turn in a paper yet.
Yeah.
Because we learned so much good stuff, and I just kind of want to change it because I want to talk about
Infinitesimals?
Yeah,
Yeah.
and I'm just like, oh.
Sure, yeah. I mean, at this point, I think all I said was to go home and start watching biographies about people.
Yeah.
So I think you could watch a biography about Leibniz or Newton or someone of your choice, and you can find something interesting.
Okay, but I'm just stuck. That's,
Infinitesimals.
yeah,
Infinite.
infinite,
Decimals.
infinite or infinite?
Infinite.
Infinite.
Decimals.
That's-
Infinite.
Infinite?
No, just infinite.
Oh, infinite,
Infinitesimals.
okay,
Infinite.
let's not do.
No, just show one more time. Infinitesimals.
Infinite decimals or
Decimals with a T.
decimals, okay, infinite
Infinitesimals. There, infinitesimal.
You should be a yoga teacher.
A yoga teacher?
Yeah.
Oh, that's funny.
That
Just
would've
the
been-
whole time breathing infinite.
Testimonials.
My wife was a yoga teacher.
Oh, that's. But, okay. Something I want to know.
Right after this, 1 to 2, or right before this for half an hour. So it's either right before or after this class. Oh, good, I want to go over what you missed. What day? Monday? Okay, I understand. Well, first of all, did you already watch the video from Monday?
Yeah, but like I said.
Oh, yeah. Oh, yeah, that's right. It was a terrible group. Well, so if not today, then either A, you could always email me your specific questions. Like, for instance, just go home and start trying the homework on the More website. And whichever one doesn't make any sense, you just email me. And then I'll email you right back with a little explanation. So that way we could do it from home. Or if you wanted to just wait until next week, we don't have school on Monday, so then it would be Wednesday, a week from now. We can meet right before after class.
Okay.
But Wednesday's a long time from now. Why don't you go home and try the email and email? I mean, sorry, try the homework and email. I would much rather that because if you send me 5 emails today, I'll send you 5 emails back. And hopefully that will be enough. Plus the video or the homework has videos. And just watching those videos might answer your question too. Okay, I think everybody's back. Well, no, not everyone's back, but I'm going to go ahead and get us started. Everyone take out a lined sheet of paper. Take out a lined sheet of paper. Make it look really nice because you can hang it up above your bed, above your pillow, or maybe in the bathroom, or in the kitchen, on your fridge. So let's title our paper, Find the Slope of a Parabola at any value x. Now, find the slope of a parabola at any value x. I really wish that I could have found you over the summer and just walked up to you and been like, hey, by the way, you're taking calculus in the fall, real quick, over the summer, go home. Find the slope of a parabola at any point x, and just let you play with that for a while. Because that's what Newton and Leibniz were wondering about. Like, gee, how do we do this? How do I find out, here's our parabola. It's going to be the most basic parabola there is, just f of x equals x squared. Right? And there they were thinking, well, gosh, the slope is always changing. I mean, here the slope is 0. Now it's positive. Now it's even more positive. Now it's even more positive. And over here it's negative, and now it's even more negative. This is a creature whose slope is constantly changing. So even if I can find the slope right here at x equals 1, as soon as I get to x equals 2, the slope is going to be different. And as soon as I get to x equals 3, the slope is going to be different again. And slope at 0, well, that's easy. The slope is 0. But now the slope at -1, that slope is also different. So how many different answers are there to find the slope of a parabola? I mean, the slope is literally different at every single point. And how many points are there on a parabola? Infinitely many. Right? So this is a big question. Find the slope of a parabola at any value of x. So any point on the graph you choose, it's going to be different. Now, we know 2 slopes so far. What are the 2 slopes on this parabola that we know for sure? What's one, Lisette? Which one?
What was the question?
Oh, what are 2 values of slope on this parabola that we know for sure? There's only 2 that we know for sure so far. At what? Yeah, this slope at the bottom. So if you look all the way at the bottom, you know the slope is 0 because it's flat. So there's one that we know at x equals 0, m equals 0. So there's one that we know. What's the other slope we know because we just calculated it? At x equals 1, we know that that slope is equal to 2. Right? So x equals 1, m equals 2. All right, folks, we've done a lot of work, and so far we only know 2 slopes on a parabola with infinitely many slopes. So we have a lot of work left to do. If we can claim total fluency over this parabola, that if you just tell me an x value, I could tell you the slope. And that's our goal. The goal is that if you just pick an x value at random, so Efren, please, choose an x value at random. 3. Okay, x equals 3. If Efren just threw out the value, x equals 3, I would want any and all of us to be able to calculate this slope at 3 in less than 1 second. And I could just say, bam, the slope is 6. Right? That's how fast I'd want everyone to be at this. And that's how fast we're all going to be. That if you could choose any random point, like even if you said right now, I choose the value -13, I can tell you the slope at -13 in less than a second. And you all will be able to do that too. Okay, so we're going to find the slope of a parabola at any value x. So let's start by writing down our method. Find the slope between x comma f of x. So that coordinate right there, x comma f of x, that's just a totally random arbitrary coordinate. In fact, I'm going to start drawing a little graph down here. That's just going to be my first coordinate. So there's my first coordinate. So I'm going to find the slope between it and what? Where should I choose my other coordinate? A little bit to the right. How far to the right? H units. So now I'm going to have my coordinate x plus h. Go up there. We'll find that other coordinate, which is there. And what's that coordinate?
With h squared.
Well, that's true. It is x plus h squared. I'm just going to keep writing it as f of x plus h for now, so that we're as general as possible. But you're right, x plus h squared. Okay, so we're going to find the slope between any random coordinate x and another coordinate h units to the right of x. So we're saying find the slope between x comma f of x and x plus h comma f of x plus h. And in this particular case, we know we're talking about a parabola, so f of x is actually x squared. But to be fair, what we've written down right here is the most general case, like if we didn't actually know what the function was yet. So let's continue on our way, finding the slope between 2 points of a general function. We don't know that it's a parabola yet, it's just some function. So let's write that down. I'm going to label this blue so everybody sees it real nice. x1, y1, x2, y2. Our slope, m equals y2 minus y1, x2 minus x1, is going to be f of x plus h minus f of x all over x plus h minus x. And what's the only thing we can do with that right now?
Cancel out the x on the bottom.
Cancel out the x's in the bottom. So what we have right here, folks, f of x plus h minus f of x over h. This is actually called something. This is called the difference quotient. It's our first tool in calculus, the difference quotient. And what it does is calculates the slope at any point on any function. That sounds like a pretty tall order. That thing right there will calculate the slope at any point on any function, because we've made it as general as possible. We're just saying for any function, pick 2 points, h units apart, find the slope. That's going to tell me the slope at that point, the point on the left. So in this particular case, f of x equals x squared. So we can rewrite this a little better. M equals, instead of f of x plus h, we can say x plus h squared minus x squared all over x plus h minus x. That's what we would have written down had we actually written it in terms of the parabola. And in fact, I can go back up to my coordinate and then write that down if I wanted to. That would be x comma x squared, and that would be x plus h comma x plus h squared. Okay, so now let's do all the algebra. What algebra do we have to do? Efren already pointed out that the x's cancel out on bottom. So now what about on top? What's x plus h squared? I would recommend going somewhere else to do a little scratch work. What's the definition of squared again? Multiply by itself. And when you multiply by itself, you're really doing FOIL. So we're going to FOIL it out first, outer, inner, last, which is x squared plus 2hx plus h squared. So now what we have is x squared plus 2hx plus h squared minus x squared.
Okay, you'll see. You'll see.
Now what can we do? We can cancel out the x squareds, and that leaves us with 2hx plus h squared all over h. And then what? It's just like the last one we did. What's our next step? Factor out our h. We've got an h out front there, so now it's 2x plus h squared. No, just h, all over h. And then what can we do? We're going to cancel out those h's, and we're left with 2x plus h. That is the slope between any 2 points on a parabola. That is, between the 2 points such that the first one is the one we're interested in, and the second one is just a little bit to the right of it. Well, we're about to find the slope of this one. So now what we do is, because we have an expression in terms of h, we take the limit as h goes to 0 of 2x plus h. And that's going to tell us the slope at this point. That's the point that we're actually finding the slope at. So what happens when we plug 0 in for h? It's just 2x. And so now what we can say for sure is, at any point on the parabola, the slope at a given point x is simply 2x. That's the slope. And I'm going to write it in a sentence. On a parabola, the slope at any point x is m equals 2x. And I would say this is our first real good, strong calculus result. That we have now found the slope of a parabola at any x value x. So if you tell me the x value, how do you calculate the slope? Just double it, 2 times x. And you'll notice that's exactly what we were doing up here, right? That's the x-coordinate, that's the slope. 0 times 2 is 0. That's the x-coordinate, that's the slope. 1 times 2 is 2. That's the x-coordinate, that's the slope. 3 times 2 is 6. So my playful example, what is the slope at x equals negative 13? What's the slope up here? Negative 23. And that's it. So if you choose any point on a parabola, you just take the x value, double it, that's the slope at that point. Does that almost sound too easy? Like, I don't know sometimes if as we look at calculus, it's no longer very impressive looking. Like, if you want to find the slope of any point on a parabola, you just take the x value and you double it, and that's the slope. But that's it. That's the result. So that's one of the first things that Newton and Leibniz did, was calculate the slope of any point on a parabola, and that was the method that they used. Now the good news is we're going to spend all next class doing this method over and over and over again. Today, this was just like a nice little gentle, how do you do, seeing how it works. And that's all I have to say about this right now. Does anyone want to ask any questions about this method? This method is called the difference quotient. You use the difference quotient to calculate the slope at any point on any function. Does that seem like a fairly long process? Maybe it's a little long. Maybe you'd call it medium long. The good news is that after we do that for a couple days, we'll learn some shortcuts. And then you can take the derivative of any function just like that, just by using a shortcut. And you don't have to use the difference quotient anymore. but we're using the difference quotient for at least a couple class periods so that you can appreciate what Newton and Leibniz went through in order to come up with this stuff. Okay? Really, truly, if no one has any other questions you want to ask about, then I want us to actually boot up our computers and do some Excel work. Here's what we're doing with Excel. We have 30 minutes. Yeah, we have 30 minutes. We're all going to boot up your computer, open up Excel. We're going to create an Excel spreadsheet. Then you will save it. And then you will, well, I suppose email it to me. Better yet, email it to yourself, because then you can have a copy at your own home computer and copy me on the email so I can see your work. So everybody go ahead and take a moment, boot up your computer. I'm assuming all the computers are going to work. Oh, good. Are the computers already on? Oh my gosh, so many of you are already on Excel. How did that happen so quickly? Were the computers already booted up? You didn't have to log in? You didn't have to. Oh, you do have to. Oh, okay. So a lot of you had already logged on. Okay, I see. You were just excited and you were already there. Okay, well, let me know if you need help finding Excel. You have it. You're getting there. You have it. We're just going to open up a blank worksheet this week. Now, I'm guessing that a lot of you have already worked with Excel. Just out of curiosity, raise your hand if you've never used Excel before in your life. Okay, there's a couple of you. That's fine. That's totally fine. I'm gonna walk us through it so we can see how it all works. Now that you have Excel open, please go ahead and I think what I want us to do is take out your section 2.1 and let's look at that particular problem. This one. Let's all take this out and have that in front of you at your desk. This was in section 2.1, number 4. So take out section 2.1, number 4. This one, if you recall, it was just a long, laborious problem. Do you have yours? You either had to type it all into your calculator over and over again. Well, no, that wasn't the solution. Typing it into your calculator over and over. Yeah, you have it. All of you have it. Section 2.1, number 4, the packet. Oh my gosh, okay. Wow, really? That's so strange. How dare they? Oh, you already logged off again? Okay, you poor thing.
Which program did you want us to?
That's it, blank workbook. Yeah. Once Excel opens up, you can just click on the blank workbook. In fact, here I'm going to do it now. So there's my data. And then here's my, where is Excel? You just type there to search for it, and there it is. Okay, so here's Excel, blank workbook. Okay, here we go. So, okay, good, you can all see. One thing we're going to do in this class is learn how to do long multi-step problems where 2 points are getting infinitely close together. Programming an Excel spreadsheet to do all that for us so that we don't have to sit there and type anything into our calculator. So an Excel spreadsheet is a really nice shortcut. So the first thing that we want to do, and I don't know if I can make this any bigger. It doesn't look like I can make it bigger, so I hope everybody can see that. Okay. Wait, there should be a way to make it bigger. How do I make this bigger, folks? I just did Control plus.
You trying to make the slot bigger?
I want this all to be bigger. Zoom. All right, that's pretty good. Sure, that's better, right? Everyone can see that much better. And likewise, I've got. Oh, I zoom my data. There's my data. Good. Oh, I'm so excited. I almost feel like this is a good classroom. All right. Not you guys. Of course, all of you are good. I meant the room itself. The room itself. The technology is working nice. Okay. So here's what I'd like us to do. We're going to, first of all, label our document. So we're going to call this sliding two coordinates infinitely close together, just for fun. And then we're going to go down and we're going to start labeling what we're going to put into our data. So we might as well define a few things. Given an interval bracket a comma b and function, in this case, h of t equals 34t minus 0.83 squared. Oh, and you know what we should all do right now? Before we get too much further and there's a power outage and we lose everything, we should save this. So you can go to Control S, or you can go up to File, Save, whatever you want to do. And I'm just going to save mine on the PC, right on the desktop. And if you want to do that too, you can. I'm going to call it JW's mat213 Excel spreadsheet. Because we're going to be using this a few times, well, we can just keep on opening up the computer to this desktop, and then the file will just be waiting for you on the desktop. So if you want, just save it right onto the desktop. And that way, every time you come to this classroom, actually, anytime you go to any classroom and you log on to your computer with your information, that document will be waiting for you. Does anyone need any help saving the document? I'll just walk around real quick. If you need help saving the document, please let me know. Everybody over here? You all saved? What happened to yours? It's still, oh, you poor gentleman. Oh, no, it is still loading. What the heck? Oh, well, slow process. Okay, but Michelle, you have one? Yeah, you do. Do you have one? Oh, good. There you are, Brandon. Okay. Did it save okay for everybody? Okay. And let's go ahead and define one more statement. We'll say the slope is m equals parenthesis f of b minus f of a divided by b minus a. Now, the first thing you'll notice in Excel is that formulas look funny because they're written sideways. They're written horizontally. If I was able to just write this in the normal way, I would have a function, there'd be my a and my b, and then that would be my coordinate a, f of a, and this would be my coordinate b, f of b. And then it would be a lot more visually compelling for you to see that the slope is therefore f of b minus f of a, all over b minus a. So I hope that looks a lot better to you. That you're like, oh yeah, that's what I prefer to see. But when we type it into Excel, it's going to write it out horizontally. And so what do you notice about the way I wrote this down? What did I do that maybe you might not have done? Or you're like, no, Mr. G, that's how I would have done it. I put an extra pair of parentheses around the numerator. You know, so f of b minus f of a is all wrapped inside parentheses. And I put parentheses around the b minus a. On the board, that would have looked like this. Would we ever write it like that on the board? That would be a little excessive with parentheses. But in Excel, you have to, so that Excel knows to keep the whole numerator and then divide it by the whole denominator. Okay. So folks, we have all of our definitions in there. Now let's go ahead and start typing in some data. So we're going to label the columns of our intervals. There's column A and there's column B. And we'll go ahead and type in the intervals that they gave us. So it's 3, 4, and then 3, 3.5, and 3, 3.1, and 3, 3.01, and 3, 3.001. And that's as far as they took it. Right? Yeah, they didn't give us anything further than that. So again, I don't want to leave anybody behind in the dust. I want to make sure everybody's still. Hey. Oh, okay. So for the 0.83, go ahead and click on the work given. See, that's a different cell. You're still in the first cell. We wrote it all in the first cell. Over here on given. There you go. So there's the whole sentence. Now click up there at the end of the T. And now you're going to do the caret symbol. That caret symbol is an exponent of 2. Very good. All right, that's all looking good. Very nice, very nice. Everybody already saved their work, right? It was very sad if you lost your whole document. Andy, you all look like you've done this before. I would save it to this PC, and then the desktop, and then call it something for your name, like Efren's. Okay, so what should we calculate next? Ultimately, we're trying to calculate the slope. So those are our A and B values. What should we calculate next? What else are we going to need to calculate? F of A and
FOB.
F of B. Wonderful. Yeah, we're going to need those too. And so now, here begins the Excel work with using this as a calculator. Instead of your TI-82, you can use this. So now everybody click in the first box below F of A. And what you're going to first type is equals. The equals button is right next to the backspace button. Just to the left of the backspace button is the equals button. So now what you write down is equals, and we're about to type in the function 34t minus 0.83t squared. But instead of a t, we're going to put an empty parenthesis, and inside the empty parenthesis, we're going to refer to the cell of where A is. Now the cell where A is, this first 3 right here, that's the cell A6. And this cell is the cell B6. So that's A6, B6, C6. The cells are all labeled according to the column they're in and the row they're in. So let's start typing this together. If I want to calculate F of A for that first A value, I'm going to write equals 34, and then you have to actually type the multiplication button, which is Shift 8. Shift 8 gives you the multiplication dot. Now parenthesis, and then what you do is you take your mouse and you go click on the 3 that you're referring to. And you'll notice that it inserts for you A6. It's referring to the cell A6. Now close that parenthesis. So now we have 34 times our first value minus 0.83 star. So once again, you have to put the multiplication. And then again a parenthesis. And we want to once again use your mouse and click on A6. And then close that parenthesis. And then use the caret button, which is Shift 6. And that way you can square it. And that is what that cell should look like. So equals 34, Shift 8 is your multiplication. Click on the cell A6. Minus 0.83, the multiplication again is Shift 8. And then parenthesis, again click on A6. And then close your parenthesis, caret button 2. That means to the power of 2. Did everyone get that typed in? Let me know if you had any complications with any of those. Did it work? And then you hit enter. And there we go. It automatically. It calculated it for us. All right. Now that you just did all that, you can still see the formula up there. All right. You can still see the formula up there, even though now all you see is a number. But technically, there's still a formula typed into it. Now, if you'd like to, well, I'm going to show you just the brute force way. Now everybody click on F of B, and it's not bad practice to go ahead and type all that again. So now what we want is to do the function, but this time we're going to refer to the number 4. So now this time it's going to be equals 34 star parenthesis, click on the cell B6, parenthesis minus 0.83, parenthesis, click on that again, parenthesis, over 2. So we basically just typed the entire thing, the exact same, except we clicked on the cell B6 instead of the cell A6. Oh, I found a typo. Where's my typo? I did forget to multiply. Thank you so much, Sadia. Thank you so much. It's so important that you use that multiplication symbol with the coefficient in front of a parenthesis. Hey, Sadia, I did that on purpose, and you caught it. Thank you. All right, so now I should be able to hit enter. Did everyone get 122.72? Yes, Simone.
I got the B column line, but it's not.
You're the what? Oh, okay, great. If one of those numbers doesn't match up, let's just look. So it's 34 and 36. Oh, it's going to be minus. Minus. So you just check the minus. Oh. Okay. Good work for everybody? Everybody has those first two numbers so far? Okay. Now, you might be saying, Mr. G, why did you just make us type all that in again? When obviously we can just click on the one that we already did, go up to the top and copy all of that, and then come over here to the next cell. I'm just gonna, oh no. Things can happen fast. There we go. So there, I'm gonna delete that. Instead of typing all that again, I could have just gone to this cell, copied the formula from up there, and then come on down here and pasted it in, and then change the formula, not A6, I could have just changed it to B6. And then change that to B6, and then I would have the same formula. So you can feel free to do that. You can always copy and paste the formula and then edit it. Okay. So far so good. Now, some of you already did it. Do we have to now type that formula in or copy and paste it to fill in all these? What do we do? Yeah, just touch it in the bottom right-hand corner. You can see there's a little solid green dot in the bottom right-hand corner. Click on that solid green dot and drag downward. And it will automatically fill it in. Do that again with the 122.72. There's a little green dot in the bottom right-hand corner. Click on it, drag it down, and it gives us all those values. All right, well now what do we need to do? We have our A, we have our B, we have our F of A, we have our F of B. Now what do we need? We're trying to calculate M. So now we can go ahead and come up with a full formula for M. So let's label our column M. And now we're going to type in a formula for M. It's kind of exciting. So it's going to be equals, first a parenthesis. Everything I'm about to type is going in the numerator. So this is just my parenthesis. And all I have to do is subtract F of B minus F of A. So I click on F of B, and then minus, and then I click on F of A, parenthesis. Again, you just click on those cells to get a reference to those cells. That's your numerator. Go ahead, Bata.
Minus.
Yeah, that is 122.72 minus 94.53. We won't click on the F of B, actually, but the two below. Did that work? And then everybody divide by, which is the backslash. It's the same as the question mark that's to the left of the shift button. And then another parenthesis. And now we have to do B minus A. So we click on the 4, and then minus, and then the A, and then close your parenthesis. And there's our slope formula. Please let me know how that's going for. Oh, I didn't even click it yet. Is it 28.19? Yeah. In case you already finished and I clicked enter. 28.19. Okay. Folks, you're all nailing this. You're doing it so well, I feel a little sheepish up here, like I'm showing you how to do something that you already know how to do. And very well, you might already know how to do it. But it's good for me to be able to walk around the room and see that you're all there. Okay, so now take that box and drag it down. So we've now finished that problem. Does anyone like this method compared to typing all those numbers into your calculator and writing it all down? This is a pretty cool method. This is really nice. Now I'm going to show you something even cooler. Even cooler, folks. What? I'm trying to remember. Everybody, let's say we wanted more data. So I'm going to do 3.0001. Was that cool? Did Did anyone see what just happened? I mean, that was really cool. I'm gonna do that again. I'm gonna delete that. If you just go on down to the, oh no. You go on down to the bottom and just put another 3, and you're like, okay, I want a point that's just 3.0001 units to the right. And bam, it just did all those calculations for you. That was cool, right, Diego? That was super cool. And then you're like, well, shoot, let's keep that going. There's 3 and there's 3.00001. And then it calculates that for you as well. And then you can do 3 and 3.1, 2, 3, 4, 5 zeros and a 1. Now, what just happened? 1, 2, 3, 4, 5, 6. Something happened, which is what we call computer error and computer rounding error. Did I type in 3? I typed in 3.000001. And here I didn't type in 3, I typed in 3.000001. And yet it rounded. And then over here, did I really get the exact same 3 answers? I mean, these are all different numbers. Did each of those actually calculate to be 29.02? No, that's rounding error. All that's rounding error. So how do we fix our rounding error? Because we don't want rounding error. Everybody grab the whole bunch of data. So click at the top left 3, drag all the way down. And then you're going to right click and go to Format Cells. So you select all those cells, right click, and then Format Cells. Everybody there with Format Cells? Once you click on Format Cells, there we go. We can go to Number. In the category, it's the second one down, Number. And now we can do decimal places. And I'm going to increase my decimal places all the way up to like 10. Because I want some more decimal places. Mo decimal places. Mo decimal places. And now if I click OK, my data looks a little worse because it's so gigantic now with all those zeros at the end. But see, I just tacked on all those zeros of precision. And now I'm able to look at the all-important last row. Right? Like it's kind of a bummer to have all these zeros over here. But this one, I really want all that precision. Because now I can really watch my slope, zooming in on a particular value. Now, I wonder, folks, I never tried this before. Do you think I could have just selected the last column? What if I go back to Format Cells and I bump this back to decimal place of 2? Oh, well, there we go. I could have left all those. We didn't have to do all those. I could have just highlighted the last column to get my accuracy back. Yeah, but see, I still don't like that because now I just lost all my accuracy here, didn't I? See, this is no good. We don't want to be confused by our Excel spreadsheet. So I'm going to go back. I'm going to give them all Format Cells, 10 decimal places of accuracy. Because I'd rather deal with the zeros than actually write down the wrong number. You have to make sure that your column is wide enough if you get a bunch of pound signs. There we go. Okay. Now, once again, now that we have all that, I can still go ahead and do another thing of data. 3.1, 2, 3, 4, 5, 6, 7 zeros. And you can see now that we're really fine-tuning our answer. So everybody want to take a guess? What do we think our actual tangent value is? What do you think it's going to be? 29.02, because I'm starting to see a trail of zeros over there. And in fact, we could just be silly, right? We could say, okay, 3.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. Whoa. Actually, maybe that's the answer. Wait a minute. I think I just broke the computer. Okay, we do approach certain limits when it comes to the computer and how many decimals of accuracy it can even handle, because every program is ultimately going to have some sort of rounding error. Yeah, there's some definite rounding error going on there. 3, 4, 5, 6, 7, 8. There we go. At some point, the calculator, the computer is going to lose its ability to track all these decimals. But it looks as though the answer is zooming in right around 29.02. And just to satisfy all of our curiosity, gosh, I don't have any paper to write on. I should have paper to write on. The actual answer, because I want us to all know, just so we can see how this process works. Okay, and what were we doing at? Oh, at 3? So 34. I want to tell everyone the true value. The actual answer is 29.02. Okay, the actual quote-unquote real answer is 29.02. So what can we gather from this experience? Oh. Is the calculator going to give us the exact answer? No, because after all, it's still a secant slope. All of these are secant slopes. What we're trying to find is the tangent slope, which is when the 2 points are infinitely close together. I did not even get these 2 points to be infinitely close together. They're only, that close together. So when we use this computer as a tool, it's going to give us answers that are awfully close, and it's going to be a lot more satisfying than doing it on a calculator. Okay, everyone hit Control S again. Save your document. And down at the very bottom left where it says Sheet 1, just to the right of that is a plus sign. Go ahead and click plus. And at the top of that one, you can write, our next grand adventure. Moo, ha, 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 ha. There. So now we're all ready for the next one. All right, so from time to time when we're going to use an Excel spreadsheet to solve a problem instead of our calculator, you'll have this document ready for you. Now, does everyone actually see it on your desktop? I see mine. It's right there. It says JW's Excel spreadsheet. It's on my desktop. You all should have it on your desktop too now. At least I hope you do.
And this, what you want us to send to you?
Huh?
You said you want us to send you something.
You know what? Right now you don't have to email me anything. That's fine. Okay. So everybody ready? Let's go back to sheet 1. That's our A. That was our B. That was the formula. That was that formula. And that was that. Okay. Everybody on the original page, start at cell A1, sliding 2 coordinates, and copy all the way down to the first row of numbers. Copy all the way down to the first row of numbers. And then hit Control-C, or save, however you want to save it. I suppose you can go, how do you actually save? You go File, Save? No, that's not right. How do you copy? Is it under, I only know the shortcut. Does anyone know how to actually copy something without a shortcut?
It's the right click.
Oh, right click? Oh, okay, yeah, either way, copy. Okay, now go to sheet 2. And actually, you can go ahead and delete our next grand adventure, moo, ha, ha, ha. And let's go ahead and paste that in. Oh, why didn't I paste? Again, copy. Sheet 2. Paste. There we go. Now, I don't know about you, but my cells are now too close together. So if you want to make all the widths of all the cells bigger simultaneously, you go up to A, you click and drag all the way over to E. So you're clicking on the actual column header. And then you can choose the right-hand side of A and make it wider. And as you make A wider, you make all of them wider. Everyone follow what I just did. If you want to make all your columns wider, you click on column A and drag all the way to column E, and then go back to column A and just make column A bigger. Because as you make A bigger, it simultaneously makes B, C, D, and E bigger. Okay, so there's our numbers. And what we're going to do here, this is sheet 2. Let's just go back up to our second line of work where it says given an interval AB. Let's edit that. Instead of the interval AB, let's do, hold on a second here. Yeah, no, still the interval AB, but our function this time is just going to be 2 squared. Just t squared, the parabola. This is the problem we already did. We just did this problem a second ago on a sheet of paper. So given the interval AB, and we've got some function t2, the slope is still that formula. And what we're going to do now is change a to 1 and b to 4. Remember doing that problem? We started off at the coordinate 1 and then the coordinate 4. So we type in 1 and 4. Now under f of a, we have to change that whole formula and just make that formula equal, parenthesis, a squared. So what I'm doing right now is I'm just editing all the work that we just did to be a different formula with different numbers. So we did the coordinate 1 and 4. I just changed f of a to be f of a, or no, a6 squared. And then I'm going to change f of b. I'm going to delete that whole formula and make it b, that point squared. And the slope already updated. There's the slope of 5. Do you remember that we calculated the slope to be 5 between those 2 points? Now I can go ahead and just start writing my next coordinates. I had the coordinate 1 and the coordinate 3. Oh, I didn't drag yet. Hold on a second, folks. We didn't drag yet. So what do I have to do? We have to highlight the whole thing and then drag downward. Does that sound like the right thing to do? And then now I can delete my 1s and my 4s. Why isn't it doing it? Jeez. Okay, I don't know if that was the best way to do it, but I dragged those columns down so they'll calculate whatever I give it. So now I can type in a 1 and a 3, and it automatically calculated that slope. And I can give it a 1 and a 2, and it calculated that slope. And I can give it a 1 and a 1.5, and it calculates that slope. I give it a 1 and a 1.1, I think we did, and a 1 and a 1.01, and a 1 and a 1.001. Sorry, I know I'm doing this part a little faster. I don't mean to lose you folks. I just know the class is about to end. I'm really just demonstrating that you can tweak a worksheet you already have and plug in a different function with different numbers. And so what was the slope that we originally calculated? Oh, I never made this bigger for you either, did I? Oh, let's make this bigger. There. What slope did we end up getting for the slope at the value of x equals 1? We got 2, didn't we? And that's what this now shows. Okay, sorry, I know I did that last one a little fast. I just wanted to show you one more quick example, and we'll continue using Excel in future classes. So thank you very much, folks. It's 12:50. I realize it's time to go. We're right on track with everything in terms of the syllabus. So let's see, let's review what's due. Next week, we don't have school on Monday, but you still have homework due for 2-1 and 2-2. So that's your verbal reminder. Your homework for 2-1 and 2-2 are still due on Monday. And I'll see you all on Wednesday. Thank you very much, folks. Hey, did you all like the Excel thing? Was that pretty cool? I hope you thought that was cool. Especially because it's such an excellent example of what we were just doing. Oh, no? Oh.